Hello students. Today I'm going to discuss infinite square well potential, very important model of potential which gives useful information about the behavior of quantum system. So what is infinite square well potential? Square potential means your particle is trapped inside a well. Inside a well means, say the length of the well is one-dimensional well. So at the boundaries, potential is infinite. So potential of infinite means these are the rigid walls, and these are the rigid walls, and particle cannot escape from the wall. So here you have a particle which is inside the well and which is doing motion left and right, but it cannot escape. It cannot escape from the uh, it cannot escape from the uh, box. So let us say this is my potential box. So mathematically, this potential box can be written as, say, this is, you have a Vx, and now you have a zero potential here between the wall. This particle is free, and here you have a 0 to xl, and otherwise your potential is infinite. Infinite means elsewhere it is infinite. Now this is the ideal situation, a imaginative model, and now we want to find what are the wave function for this particle and what are the energies of this particle. So let us calculate. So we have a Schrodinger equation. Time independent Schrodinger equation. First we are solving. This is the minus h cut square del 2 psi upon del x square Vx psi equal to E psi, that is Si equal to Si equal to E psi, Si equal to E psi. So you have equation minus h cut square 2m del 2 psi upon del x square Vx psi equal to E psi. Now inside the box V0, so I can write between 0 to L, potential energy is 0. So this equation becomes minus h cut square del 2 psi upon del x square equal to E psi. Now if you solve it further, uh, I can write here this del 2 psi upon del x square will be equal to minus 2me upon h cut square psi, and this I'm writing as a k square psi, where k is what? K is your 2me upon h cut square. Now this here, this k is positive, e is positive. Okay, in my last problem we have shown that for a normalization solution, my total energy for bound state cannot be less than less than V minimum. So V minimum is here 0. That means my energy has to be positive. So here E is positive. Inside the box, your E is positive. So this K is also positive. Now if you see this equation, you have this equation. This is just like a simple harmonic motion equation where you have a del 2y upon del x square equal to plus omega square x y. So this is like so the solution of this equation will be psi x will be equal to simple harmonic motion solutions sin kx plus b cos kx. Now in order to solve this one, we need to apply the boundary conditions here. Now, boundary conditions on psi. So psi here is 0 because here B is infinite. B is infinite. So particle cannot be escape. So particle cannot be here. So here psi should be 0. Here psi should be 0. So that means I can write here psi 0 means this is 0. Psi 0 here at the boundary. So at psi x is equal to 0, psi is 0. This is 0. So put it 0 here at x is equal to 0, at x is equal to 0, x is equal to 0. So now put it 0 here. So this term becomes 0. This term becomes 1, cos 0, 1. So only this gives me b0. So now my wave functions becomes sine. This term completely becomes 0. You have only a sine kx. Now let us solve it further. So now another boundary condition at x is equal to L. At x is equal to L. Again, your psi x L is 0. So this gives me a sine KL equals to 0. Substituting here. Now this gives me KL equals to n pi, where n is what? N is 0, plus minus 1, plus minus 2, so on. Now what should the values we should take here? Now here I can take a also 0. A sin KL 0 means either this 0 or this 0. But if I take a equal to 0, my wave functions becomes 0, which is not normalizable. Okay, which is not this is a trivial solution. A is equal to 0 means everything is 0. Then what for you solving? So here a we cannot take 0. We can take now this KL equal to n pi. Okay. Now this KL equal to n pi. Now again we will not use a 0, and if you take plus minus 1, so if you take sine here, sine plus minus 1, sine minus x is equal to minus sine x. So this is not giving any new solutions. A this sine minus x, a will be sine minus x will be minus sine x. So a we can include in the constant. So I am taking only positive value. So I will take KL equals to, or my K is equal to n pi by L, and I will use only n from positive values 1, 2, 3, 4, 5. Now I know what is my K. So K square become n square pi square L square, and K square is my 2m E upon h cut square. So this become n square pi square L square. So this gives me the energy of the particle. This is n square pi square h cut square 2m L square 2m L square. So these are the possible energies of the particle when a particle is trapped in this kind of potential. So this is very useful result. So whenever you bound a particle in one dimension, or a particle is, whenever its motion is restricted, you can see the energy levels become quantized. So you have now particle energy. If I take this box, so V infinite, so 0 L. If I say this is the ground state energy of particle E1, if I take E1 here, if I take E1, so my E1 will be ground state energy. This will be my ground state, will be pi square h cut square 2m square. So these level also can be written as a n square E1. So my next table will be 4E1. Next table will be my 4E1. I'm writing energy level. This is 4E1, and this is my energy level E1, and this is my energy level E2. Next energy level E2. Similarly, if I take E3, that will be 9E1. 9E1. And like this, if I take the E4, that will be 16E1. So these are the discrete level, and we can easily find the difference between two energy level using this equation. So now these are the discrete. If I take this L, if my L is keep on increasing, if my L is keep on increasing, like if I take this is a I'm taking example of a quantum one-dimensional box where length may be in, say, in nanometer or angstrom. If I take this length is in a meter, then the gap between these level will decrease, and they will like become continuous level, like you have in your classical box, or this will be like a classical mechanics. So let us calculate now. So we can calculate the say gap between two levels. So what is the gap will be between the two levels will be En plus 1. So n plus 1 square E1 minus n square E1. So this will be n plus 1 square minus n square E1, and this is between the gap will be, see, n square plus 2n plus 1 minus n square E1, and this is cancels out, this become 2n plus 1. Now E1 is h cut square 2ml square. Now this gap delta E is inversely proportional to the length square. If length is in angstrom nanometer, then you will get the uh, we will get the discrete levels. As lengths keep on increasing, it goes in centimeter and meter, then the difference between the two levels will be keep on decreasing, and they will become like a continuous levels. So this is the one thing. And now let us find the wave function. Let us talk about the wave function. So what is the wave function? We say wave function, we have seen the wave function is sine x is equal to a sine kx. So let us normalize this wave function. So if I normalize this wave function, I'll get mod of a square 0 to L sine square kx dx equal to 1. And if you solve this one, say this mod of a square, it will be 1 minus cos 2x, 1 minus cos 2 kx upon 2 dx equal to 1. And now mod of a square, if I solve this one, 1 by 2 is here. The box is 0 to L. And now you have a x here. X minus, if you take cos 2kx, this will be sine 2kx integration. And you have a 2k here. And if you use now 0 to L length, 0 to L length, now what we can write here? So say, so k first we have to write a k as a we know what is the k value of k here. So value of k is your n pi. Okay, so if you have to put the value of k here, so k is here basically a sine n pi by L x. So here I will become x minus sine 2 n pi upon L x, and then you have a 2k here, 2k here, so 2 to cancel. So n pi, n pi also, n pi by L. Here you have n pi by L. Sorry. So you have a 2n pi by L here, 2n pi by L here, and bottom you or bottom also you have 2n pi by L. Now if I take the limit here, so this will be L. If you take L cancel, so this will be always 0. And for 0 is also 0. So this will give you only a of mod square 2. This is a very well-known result. So if I solve this one, this will give me equals to 1. So my a will be root 2 by L. Okay. So you can put it first, use this function instead of this one. And now if you integrate simple normalization, so you'll get the a value root 2 by L. So now my function becomes, sine x root 2a sine n pi by L x. This is my function. Now let us draw the functions. Now let us draw the functions. So if I draw the functions 0 to L, ground state, you have a n equal to 1, so this will be my function. Similarly, if I say n equal to 2, then this will be like this way. And similarly, if I take now L equal to second excited state, so this should be, I'm not drawing properly. Let me draw a symmetric way. So say this is my, and this is the middle of the box. So this is the 0, this is the L. So say this is my ground state. This will be my first excited state. Okay. And similarly, if you can draw the second excited state. Second excited state will be called, second state will be like this, like this. That is, L will be first, for first one, L will be L by 2. For second, L will be lambda. For third, we can easily prove this relation. L will be 3 lambda by 2. That is, L is equal to n lambda. So these are the wave function psi naught, psi 1, and psi 2. And we see these with respect to the center of the wall. With respect to the center of the wall, these functions are either even or odd. So when we know in quantum mechanics, whenever you have a symmetric potential, your wave functions are either even or odd. So this is the even function, this is the odd function, then this is again even function. Even function means if you take psi minus x equal to b, it will be always equal to psi x. If psi minus x is equal to minus psi x, then these are called odd functions. These are even functions. These are even functions. And you see, ground state has a no zero. That means wave function has a node of zeros. That means there is a no node. If you go to first excited state is the one node. Second excited state has a two nodes. Similarly, if you go third excited state, third excited will be three nodes. So as you increase energy, as the energy increases, the number of zeros of the wave function or the number of nodes of the wave function also increases. So the first property is the with respect to the this center, you have a even and your wave functions are either even or either odd, and then you have number of nodes increases as you go from ground state to the higher energy levels. Number of nodes also increases, and now we can easily prove also that these wave functions are orthonormal. These wave function 2 upon a sine n pi x upon L, and these are psi star n psi star n psi m dx. If I solve this function, this is equal to delta nm. So if n is not equal to, if n is equal to m, then this will give you, this function will give you the value equal to 1. If n is not equal to m, then this will be 0. So these functions are orthonormal, and we know in quantum mechanics orthonormal functions are very useful if I want to expand a function. If I want to expand any function in terms of these wave functions. So for mathematical simplicity, this provides the mathematical simplicity whenever I'm going to expand any function in the basis of these functions. So these are the Schrodinger equation solution, and we are seeing Schrodinger equation in time independent Schrodinger equation providing the infinite solutions, and we see this in these solutions are orthonormal also, and we can now express any function psi n as a summation of these functions. Any function psi x, any function psi x can be represented as a superposition of these functions. This is called spectral decomposition, or you call it as a Fourier series, because it's a sine function. So we know any function can be represented as a sine and in terms of sine and cosine in a Fourier series. So this is, so we can represent any function like this. Now what is my psi, and this is a root upon a sine n pi x upon L, and here an can be calculated using the orthonormality conditions. We know that psi x and psi n x, if I integrate this one, this will be equal to, because these functions are orthonormal, so only if I take the component of psi n on psi x, only this term will be remaining. So this will be equal to an. We have talked this thing earlier many times. So I can find the an, constant an, using this orthonormality conditions. Okay, so now we have an also. We can expand in terms of psi n, and if I want to write the stationary solutions psi xt, so psi xt will be simply an psi n e power minus iota en upon h cut t, we can write. So my psi xt will be an psi n. You know psi n, what is psi n? Psi n is root 2 upon a sine n pi x upon L e power minus iota n square pi square h cut cancels, and 2 m L square into t. This cancels, so n square pi square 2 ml square t. So these are my stationary state solution for a particle in a box. Okay, so here we have solved a box which is length is 0 to L. In my next class, I am going to solve the same problem by keeping the box as a symmetric. So if I say my length is minus a to a, then this becomes 0. So that will become symmetric potential. In my next class, we will solve we'll just solve the symmetric potential. So I'm stopping here. Thank you very much.